we have to study the concept of free valence, pi bond order, and charge density according to Huckel molecular orbital theory. The first one is the concept of free valence. The concept of free valence at a carbon atom is used as an index to indicate the ease of attack by free radicals at that carbon. This free valence index gives a measure of chemical reactivity. The carbon atom which has the largest value of free valence index will be the most reactive in that molecule. The free valence index, which is represented by Fr at a carbon atom R, is defined as the difference between the maximum bond orders, that is Nmax, around a carbon atom and the total calculated bond orders, that is Nr, around the atom R in a molecule. That is Fr, that is equal to Nmax minus Nr. The maximum value of N, that is Nmax, so far found in unsaturated carbon compounds is 4.732, which is associated with the central carbon atom of trimethylene methane. Therefore, the free valence of a carbon atom in a molecule is given as Fr, that is equal to 4.732 minus Nr. With these values, the free valence index of different carbon atoms can be computed. This concept, the free valence concept, provides quantum mechanical interpretation of Thales' theory of partial valency used in classical organic chemistry. From molecular orbital calculations, the free radicals have free valence values equal to or greater than 1. Values of 0.08 are associated with the terminal carbon atom in a chain. The values around 0.4 are observed for aromatic carbon atoms, and in the case of internal atoms, very small values of free valence are observed. The usual way of representing free valence is by an arrow diverging from the atom with a numerical value of free valence written at its head. For example, butadiene can be represented as follows. It has 4 carbon atoms, C1, C2, C3 and C4. The free valence of C1 is represented by using an arrow, and at the arrowhead its value, that is free valence value, is given as 0.8376. Similarly, C2, the free valence value is 0.3903. For C3, the free valence value is 0.3903, and also C4, the free valence value is given as 0.8376. These values tells us that butadiene could well be more reactive to neutral nonpolar reagents such as free radicals at the terminal 1,4 carbon atoms than the central 2,3 carbon atoms. Here the neutral nonpolar reagents are specified here so as to avoid the charge distribution effects. Next we have to study the charge density. The HMO coefficient, that is from the HMO, it is also called eigenvectors in that equation, HMO equation, in Huckel calculations can be transformed into derived physical properties of molecules. One of these quantities is the charge density. The magnitude of the coefficient of an orbital, that is Cij, at a carbon atom Ci gives a relative amplitude of the wave function at that atom. Since we know that the square of the wave function is the probability function, the square of the eigenvector coefficient gives the relative probability of finding the electron within an orbital j near the carbon atom I. This is a measure of the relative charge density of the molecule. The point in a molecule where the probability of finding the electrons is maximum, having a large value of charge density, and a portion of the molecule at which the electrons are not likely to be found is positively charged. There may be one or two electrons in an orbital, that is the number of electrons, that is n is equal to 1 or 2. The unoccupied, it is also called virtual orbitals, make of course no contribution to the charge density. In a pi system, a neutral carbon atom is associated with an electron charge density of 1.00. To obtain the charge density Qi at the carbon atom Ci, we must sum over all occupied or partially occupied orbitals and subtract the results from 1. That is Qi, that is equal to 1 minus sigma n Ci square, where sigma n Ci square is the total electron density at Ci. For example, in the case of ethylene, there are two carbon atoms, the Q1 at C1 that is equal to 1 minus 1 that is equal to 0, Q1 at C2 that is equal to 1 minus 1 is equal to 0. For allyl system, it is represented by C double bond C, single bond C plus, that is allyl carbocation. Here there are three carbon atoms, so the Q charge density at Q1, the charge density at C1 that is equal to 1 minus 0.5 that is equal to 0.5. Therefore, and also the charge density at C2 that is equal to 1 minus 1 that is equal to 0. And the charge density at third carbon atom C3 that is equal to 1 minus 0.5 that is equal to 0.5. Thus, in ethylene, each carbon atom is neutral, whereas in allyl cation, the positive charge is distributed equally among the terminal carbon atoms and the central carbon atom is neutral. Next, we have to study the pi bond order. The HMO coefficients can be used to calculate the pi distribution of electrons in the bonds also. If Aij and Aik are the HMO coefficients of the carbon atoms Cj and Ck, which are connecting carbon atoms, that is adjacent carbon atoms, and n is the number of electrons in the single orbital, that is in a single orbital we have 2 electrons, it may be 1 or 2. Then the pi bond order Pjk, that is given by the equation Pjk, that is equal to sigma of n Aij Aik. The bond order thus calculated is known as the mobile bond order or the Coulson bond order because it was derived by the scientist Coulson. Larger the coefficient, the greater will be the pi bond order. If one of the coefficient is large, the other is small, it will imply that the electrons are chiefly located around one of the nuclei and not between them. If one of the coefficient Aij or Aik is 0, it will indicate a node at the atom, and Pij will be 0 in conformity with the non-bonding situation. If the coefficient Aij and Aik are opposite signs, it will indicate a node between the atoms Cj and Ck, and a negative pi bond order in agreement with the antibonding situation. Let us study the calculation of pi bond order of the ground state of butadiene molecule. In the ground state of butadiene, the HMO calculations gives the first 4 molecular orbitals, that is psi1, psi2, psi3 and psi4. There are 4 electrons. These 4 electrons are occupied in the first 2 states, that is psi1 and psi2. the structure is represented by CH2 double bond, CH single bonds, double bond, CH2. Therefore, the pi bond between the carbon atoms 1 and 2, that is P12, that is equal to 2 into 0.3717 into 0.6017 plus 2 into 0.6015 into 0.3717. That is, here is a total of 4 electrons, and 4 electron is occupied between the two molecular orbitals psi1 and psi2, 2 electrons in the psi1 and 2 electrons in the psi2. So it is the sum of the pi bond orders of psi1 and psi2, that is, the electrons are present in the 1 and 2 carbon atoms of psi1 and psi2. Therefore, P12 is equal to 0.89944. Similarly, the pi bond order between the carbon atoms 2 and 3 is given by P23, that is equal to 0.4473. And also the pi bond order between the carbon atom 3 and 4 is given by 0.8944. This result shows that the pi bond order is in between 0 and 1, meaning that each of these 3 bonds is neither a full double bond nor a single bond. That is, all have partial double bond character. And also the P12 is equal to P34, which is greater than P23. This means that the terminal bonds C1, C2 and C3, C4 are more double bond character than the central C2, C3 bond. Also, the terminal bonds C1, C2 and C3, C4 should be shorter than the central bond C2, C3 but longer than the olefinic C double bond C bond. References: Quantum Chemistry, P.K. Prasad, R.K. Prasad, New Age International Private Limited. Introductory Quantum Chemistry, A.K. Chandra, McGraw-Hill Education India Private Limited. Computational Chemistry and Molecular Modeling, Principles, Applications, K. Ramachandran, G. Deepa, K. Nambudiri, Springer.